Today's speaker is Dave Russell. He is second time around. Thank you. He's a principal of Global Environmental Operations Inc. in Livermore. For more than 3 decades, Global Environmental Operations has provided expertise in air and water pollution, solid hazardous waste control, process engineering, radioactive and organic contamination remediation worldwide. He is familiar with all aspects of chemical plant, petroleum, agricultural plants, and environmental challenges, including hazardous waste work and regulatory cleanups. He's written extensively on subjects dealing with environmental control in the chemical and petroleum industries, articles on hazardous waste management, property transfer liabilities and assessments, and other environmental topics. He's a past faculty instructor in environmental engineering at Southern Tech, KSU now. He's provided technical training and addressed conferences in North America, Europe, and the Middle East. He's authored several books and articles in technical journals. He received his Bachelor of Science in Civil Engineering from the University of Illinois at Urbana-Champaign, Master's in Civil Engineering from West Virginia University, and has pursued additional graduate studies at the State University of New York, Baltimore. He's a registered professional engineer in multiple states, served as expert witness, and he is listed in the Who's Who in Engineering, active in numerous professional societies. Please join me. Round of applause.
Evening all. I want to talk to you a little bit about computer modeling and environmental management, and I promise not to go too deep into partial differentials. I know you've all had the courses, but I promise not to go too deep into partial differentials, because if I do, I will just hear the sound of eyelids closing. All right. Where and why do we need computers in the environmental field? Well, pre-1960, and some of you are old enough to remember that, most understanding was by hydrodynamic modeling, or in some cases graphical modeling. Where the models were used, they were very cumbersome, and some of you may remember trying to perform things like moment distribution or closing survey traverses using a set of 12-place log tables, an old repeating mechanical calculator, and maybe your slide rule. I still have a slide rule. So, as a result, the calculations took hours and the results were crude. Solutions to the partial differential equations were all analytical. With the advent of the computer, our knowledge exploded. Analytical chemistry exploded. Detection limits used to be at 5 to 10 milligrams per liter for many compounds. Now, they're measured in terms of 0.01 parts per billion. And that's 0.01 part per billion is 1/1000th of a milligram per liter. There's an old story about a guy who walks into a bar and he tells the bartender he wants a dry martini. He says, "Here's how I want you to make it. I want you to take a clean glass, I want you to rinse it out with gin, throw that out, put in new gin, and then whisper vermouth across the top of the glass." The guy does. The guy takes one sip. He turns to the bartender and says, "Loud enough." And that's where we are. That's where we are with our chemistry. That's where we are with a lot of our analytical abilities. All right, with the explosion of the calculation ability, our understanding and ability to make models and to understand the environment also exploded. We now started to look at things that we didn't know were even there before. Having said that, most environmental systems are complex and cannot be expressed in single or simple algebraic equations, but most use differential calculus, partial differential equations, or PDEs. Lots of examples. Air modeling. Many large programs and massive databases. Rainfall and meteorology and weather modeling. Oh Lord, yes. Groundwater modeling. Water distribution modeling. Sewer collection system and drainage modeling. And the biological equations.
Would you add to that watershed calculation?
Yes, definitely. That would go in with the combination of rainfall, meteorology, and weather. I would put watershed in there because it is, by and large, a function of having meteoric water come in and get into the groundwater or into the streams and so on and so forth. When you start dealing with that, you are definitely in the area of second-degree partial differential equations.
The Feds used to have a scale model of the Mississippi River Basin.
It's out in California. Oh, I'm thinking of the Bay model. If you go out to San Francisco, just north of San Francisco, there is a huge room. It must be 500 by 500 feet. It's a scale model of the San Francisco Bay that they actually use to plot rainfall and tidal flows and so on and so forth. So now they no longer use that. It's just a museum piece. They're doing everything digitally. So, all right. Many of these models require unique numerical solutions because the solutions are too difficult or impossible to obtain analytically. Water distribution and wastewater collection systems are solved using relaxation and superposition techniques. Techniques, surprisingly enough, that were developed by Hardy Cross in the 1930s and widely used in structural analysis and some flow problems. It's good for water distribution systems, anything that you have. For example, you can use it for heat transfer up to a point. Ordinary differential equations, some can be solved directly, others not. Generally, they have one variable. Partial differential equations, a problem with multiple variables, cannot be solved directly, but approximate solutions by several methods often involve the rate of change of the variable with time. And I have a little example here. An ordinary differential equation has usually one independent variable, whereas a partial differential equation, you can see that you have the terms du dt, a constant, and this second degree partial of u with regard to two different directions. So they are a lot more difficult to solve. Let's see if I've done that. Yeah, this is, for example, an air pollutant. This is Fick's second law of diffusion. When you have heat flow, and that's where it's mostly used in X and Y plane. What happens is, and certain types of, let's say, for example, if you're looking at a membrane, and a membrane, the concentration variation across a membrane would be all in Fick's law. It's a nasty little equation, but solvable. Now, the way that they solve some of these equations, they use forward, backward, and central differences to approximate. For ordinary differential equations, we need to know the initial values to be able to compute the solution. For partial differential equations, we need to know the initial value plus behavior at the boundary. For example, does the boundary have a solution or have a fixed constant? Does the boundary have a gradient? And in most environmental applications, we're into these second order partial differentials. Air quality, for example, air quality monitoring is often involves not only stack testing, but to compute downwind concentrations for particulates and gases, CO, SO2, NOx, and so forth. But particulate less than 10 microns. Some dusts, particles that the EPA is very concerned about are as small as 0.2 of a micron. And when you're down at that size, basically it doesn't settle. The problem with that is it's respirable and it collects in your lungs. Atmospheric pollutions are hard to model because of things like atmospheric turbulence. Now, how many of you here have ever dealt with boundary layer and shear problems? A couple. And you're talking about mixing length and things like that. It can be nasty. Eddy currents, chemical composition, greenhouse gases and everything else, heat flux or solar and natural changes, air density with viscosity and with height, and reflection from the ground sources, plus the velocity due to wind. A typical sort of application would look something like this. Air pollution modeling, you have, this makes a fundamental assumption that you have a Gaussian type distribution in here somewhere in this plume. And the thing is that you can look at smokestacks and you can see some of them going up like this. You can see the general parameters and outlines. But the question you're trying to answer may be down here in this range, right at the bottom where people are breathing it. Here's another one with fluctuations and plumes or puffs, the effect of rainfall and all that. This would be very interesting and very complex. It winds up being some of the air pollution modeling. If you're going to start with a new plant, in some cases, you may have to go in the assumed downwind direction. Run some models as far as what you anticipate the stack height is going to be. Compute where the ground impact might be the greatest, and then set up and run modeling stations or monitoring stations at those locations and run them for 3 or 4 years just to get enough data to be able to confirm the model that you have, and then you can get your environmental permit. It's nasty. All right. Typical modeling equations for something like that, where F is a crosswind parameter, sigma is a dispersion estimate of the plume, and G's are vertical dispersion without ground reflection. And you have a couple of other constants. You have an emission rate, downwind velocity, the height above ground, center line, and the height of the observer above the ground. Computer solution and lots of computation.
Yes, it's delicious.
So, all right, Moving on to something a little more, slightly more friendly. Groundwater modeling is equally challenging. You have the simplified figure will indicate you have your recharge area, you have the movement of water through a porous medium, and we'll come to the equations on that. You have the possibility of recharge from things like wells or streams and rivers and runoff. You have the possibility of suspended or perched water tables, and you can see that these are aquicludes. And when you try and put this all together, the thing about groundwater modeling is that you can't afford to get the information, all the information you really like to have. You're always operating in a strange environment, just because every time you run one of these wells down, you're talking $30 to $40 a foot, maybe more. And the analyses for something like groundwater, I've seen them run as high as $200 and $300 per sample. I had a case year and a half ago down in Peach County, where we were running $150 per sample. Yeah, and it was pesticides. So, all right.
This would have to be done before you get your permits to use build, right?
Yeah.
You have to do this. You get
Absolutely,
permits
yes. Before you get your permits, in some cases, the site I was working with was what they call a brownfield. There had been contamination there. There was an old airport landing strip where they had a crop duster, and the crop duster used to dump out his tanks, and it was all kinds of super nasty stuff. And they had done some cleanup, and there's a company down there that wants to buy the land, but doesn't want the liability of potential exposure for this. And we documented the extent of the boundary or of the surface plumes, and then work with them and work with the state to say, oh yeah, okay, here's what the groundwater looks like. We're going to draw a boundary around the site that nobody will use, and we'll put that in a permanent covenant on the site, so that nobody will ever be able to draw groundwater out of this area, just in case. So it gets rather tricky. All right, I mentioned Darcy's law. Darcy's law is the fundamental law for groundwater movement. The formula there is K is equal to quantity, and the length L, and the area. So you're talking about the difference in water elevations. Now, where this gets to be fun is when you start to talk about the rate of change of this. This rapidly becomes a first and second order differential equation. For example, when you pull water out of a well, you create a cone of depression. And that cone of depression changes with time and your drawdown. What's happening is you have a certain amount of water, the speed will vary. And then when you start looking at something like putting in some contamination here, let's say for example, how long will it take till it's affecting you here? That could be months, it could be years. You're trying to figure it out, again, with highly limited data.
You use a lot of concepts that you say, well, this one should be weather-wise and everything else that are going to influence that data over the years.
There's a term for it. It's called a swag. Most everybody here knows what the term stands for.
Oh, yeah.
I think it should be defined.
A scientific wild ass guess. All right. What did I do? Wrong way. There we go. Consider the various sources and withdrawal plus the transport equations. And here we ran into, right in here, we ran into a problem because the equation did not translate. But trust me when I say it's a second degree partial differential equation in 3 dimensions, x, y, and z. And each of those terms is partial whatever squared over a appropriate boundary. So variables include permeabilities in one to 3 directions, leaky and discontinuous aquifers, which I mentioned, grain size of the aquifer, hydraulic gradient, movement, withdrawals and their effects, type and solubility of pollution, density, viscosity, two-phase flow, you name it. Phase interactions and solubilities. Let me just say that it's a mess. All right. Since many second degree PDEs cannot be solved directly, numerical solutions such as finite element and finite difference are often used. But there's a caveat. Finite difference solutions are good and easy to program. They are useful where boundaries are regular and preferably regular, such as linear cubes and rectangles. Those of you who are structural engineers remember moment distribution that was done by Hardy Cross. He was a structural engineer, and they found out he helped develop the whole idea of successive relaxation. And it's been adapted for certain things. For example, if you're analyzing a water network of distribution piping, you can use a Hardy Cross type technique. So, all right. The second thing is finite element. Now, finite element was first developed in 1928, but they can be used for irregularly shaped or fluid domains, but the boundary and internal conditions are extremely difficult and time-consuming to program. For example, for a fluid element, you have to solve the shape, mass and heat transfer and boundary conditions for each individual element in 3 dimensions at each boundary. This leads to very large but sparse arrays which chew up lots and lots and lots of computer time. Pardon me. So that there are some of the methods we have of solving second degree partials, and I said I wouldn't get heavily into math. More than one type, generally speaking. There's parabolic, elliptical, linear, and nonlinear, and hyperbolic, and so on. Each has a preferential solution. The math is complex and exhaustively intense. Too heavy for this presentation. The preferred method for many differential equation solvings is Runcutter. It's the fastest method. It uses a modified Taylor expansion for 4 terms. You can use, as I mentioned before, finite difference, backwards and forwards. Most finite difference examples are based on modified Taylor expansion series. They're somewhat slower than Runcutter, but also effective. Ideally, what you want to have is you want to have the option to be able to take different types of analytical solutions and maybe use them simultaneously. For example, if you're going to set up a finite element, just take a look at that for a second. Your terms here are density, velocity, delta y, which is the change in y, delta z is the change in z, in 3 dimensions. And it just gets, like I say, it just gets very, very, very messy. I've got 3 or 4 books on it at home, and I sit down periodically when I feel the need to be a real masochist, and then wind up pounding my head up against the wall after a very short period of time. The more complex the problem, the more difficult it is to solve. Specific problems have specific solutions. Meeting multiple boundary conditions can be challenging. You don't superimpose additional elements in your problem because it soon becomes unworkable. The size of the elements is also critical. The problem can blow up if the time and space elements are too small. For example, one guy I'm acquainted with and working with had a finite element solution for biological equations. And it involves the diffusion equations for cells and biology. It required 6 weeks of analysis before the modeler gave up, and that's 6 weeks of solid computer time before the modeler gave up and reconfigured it because he had his element sizes too small. He was going to get something, but it was going to take several more weeks. And he just, at that point, he gave up and reconfigured.
These are big computers that are paying by the hour or minute or what?
Yeah, by the minute. So, all right, another solution is to organize some of the equations into matrix arrays and use existing libraries to help solve the matrices and produce solutions. There is a need to keep the time and distance steps small, or instability results. This leads to very, very large sparse arrays. And by a sparse array, there's lots and lots of zeros. And you'll see a 1 here, a 3 there, or whatever, just kind of scattered all throughout the whole thing. But it doesn't, it's mostly zeros, but it still chews up an awful lot of computer time. Several of the larger computer systems are using networks, and most of this stuff is what we used to think of as mainframe type stuff. So you're talking, for serious modeling, you're talking MathCAD and some of the major computer software programs.
You're talking very small time,
Finite elements, yeah.
how much? What's very small?
That can give you a strange but accurate answer. It depends upon, let's say, it depends upon the size of the grid you set up. This problem I mentioned, this guy was trying to model an area that was, I think it was 8 feet wide, 5 feet deep, and 30 feet long. And he tried to model it, and just the heat and mass balance conditions were just too much for him. And 6 weeks worth of computer time just blew up. A good finite element model you're talking in terms of thousands of dollars, and most of that is computer time.
So he's operating in inches or feet?
He's operating in feet, and he was, I forget exactly how tight his grid was, but he was trying to really define some of this. He was an experienced modeler. He just made a mistake. He guessed wrong on the size of the guessed wrong on the size of the element. And the thing is that the danger is if you get your elements too large, your model goes bluey and just blows up on you. So you've got this kind of interesting balance, and you kind of sit there with your fingers crossed for a while and hope that you got it about right. All right. In physics, chemistry, and increasingly biology, they are relying on matrix solutions for complex and interrelated ordinary differential equations and partial differential equations, where rates of transfer are involved. And the thing is, we'll come to that in a second. One of the things that they use is what they call a Gaussian or a Peterson matrix, a formulation of a square matrix with augmented columns to express the rates of reaction. So you have A plus B transforming into C, and you've got some rate in here between A plus B and C, and then you may have some biologicals. Let me go to the next slide and I'll show you. One of the ways in which biological models are solved is the Gaussian-Peterson matrix, such as those involving chemical reaction plus bacterial action. And what you have there is, for example, A plus 2B goes into a product S, and then this is a reversible reaction. Another compound, E, goes with, combines with S and makes ES, and energy, and then you get energy plus P. The second equation represents a bacterial reaction transformation. And the analysis is a simple equation. Looks like this. Yeah. And this is the Peterson matrix. And you can see how they set the thing up. First order of S from A to B, A, those are the coefficients of A, coefficients of B, coefficients of S, and then the other things are zero. But there's a rate coefficient there. It's straight in chemistry. P2 formation of ES from E and S, S, E, ES. So actually what happens is this and this disappear and form this. And that has a rate coefficient. And so on. And so what you wind up looking is setting up this type of array with this matrix as these coefficients. And then you can solve that by matrix multiplication. I haven't seen any heads nod off, so I guess I'm doing okay. One of the most common use of biological equations in the Peterson matrix is for sewage systems, activated sludge. The activated sludge process was first developed in 1914 by Artem and Lockett. Since the mid-1970s, the emphasis has been on better treatment, nutrient removal of nitrogen and phosphorus, water reuse, and removal of traces of personal care products. The result is that wastewater treatment plants are starting to look more like advanced chemical plants. Remember what we discussed about the second order PDEs associated with the diffusion? Well, lots of the biological equations have them embedded because of the transport of chemicals across the cell membrane. Just a quick aside here to show you how far we've come. How many of you are aware of the big wastewater treatment plant up at Mala, Georgia, the Gwinnett plant? You know where that effluent goes? Back in Lake Lanier.
About 10 years ago, we toured that facility.
Okay.
The Roy Hill plant?
Yeah, I think that's what it is. But the water quality coming out of that plant is actually better than the water quality in Lake Lanier. So we are recycling water. That plant currently, as of information I got the other day, is running about 20 million gallons a day. Has a capacity ultimately that will go to maybe 60 million gallons a day as Gwinnett grows.
You're taking the water just from the lake, it's not coming in from a bad source.
No, this is sewage.
Sewage, into sewage.
It is another bad
Wastewater.
source.
Wastewater from your house, from your toilet, from whatever, being collected, pumped up to that facility, treated at that facility, and then after several steps of treatment, then they remove the nitrogen, they remove the carbon, the phosphorus, disinfect it. It's literally good enough to drink, but then they dump it back into Lake Lanier, and the water quality is actually better than that coming out of the water quality in Lake Lanier itself.
And the drinking water is coming from Lake Lanier also, right? So that
Yeah,
it's not adding water to the lake.
well, yeah, you're basically, we're drinking recycled water in some way, shape, or form. But that's not atypical.
Is that always the case, though? I mean, has it been that
Well,
way forever?
yes and no, but let's say, for example, out in Los Angeles, I believe, they have had a groundwater injection system there where they've taken their secondary treated effluent and they've injected it into the wells along the coast because they're pulling water out of the ground. And what they're getting is they've changed the hydraulic gradient such that they're starting to get saltwater intrusions into their drinking water wells. So they pump this water down, change the hydraulic gradient, and then they have to treat the water again. And so they are drinking some recycled water. Yeah.
And there's application now.
Classic example is the gradient going down the Mississippi.
Go ahead.
Oh, I mean,
Yeah.
people up in the north are drinking stream water and
People
recycling it
down further are drinking recycled water. Yes.
It grows
Yes.
and it grows.
But this is more and more common, and it's getting to be more and more, and so there's a demand.
This worst problem is these disposable, flushable paper towels that you can toss down are not dissolving before they get to the recycling plant.
That's more of a physical problem,
Yeah.
and it causes sewer blockages and things like that. And grease and oil
Right.
is also a huge problem. There is a problem with plastics. But here's what a typical activated sludge treatment works look like. You've seen the one up at Gwinnett. This is just a local. All right. The International Water Association, which is out of London, and a number of European universities developed a model set of protocols for monitoring and modeling wastewater treatment on a static or dynamic basis. These models are referred to as ASM, which is Activated Sludge Model 1 through 3, an ADM, Anaerobic Digestion Model, and these models have been around for about 15 years, maybe 20 years, some of them or more, and they've been refined and so on and so forth. But if you take an idealized wastewater treatment system, just to give you an idea, this is what you're looking at. Now, influent, that is one contaminant. That may be another, this would be volume, and that would be suspended solids. So, come into the aeration tank, treated, the bacteria work on it, run it into a secondary clarifier, remove the suspended solids, recycle or suspended solids back in. Then you have the effluent coming off of that. And here's where you waste your sludge. Activated sludge system is relatively straightforward until one starts considering the bacterial reactions, growth rates, and oxygen chemical transfer rates, the different types of bacteria, and changes in the bacterial populations. And believe me, all those do make a difference as far as what's taken out of the wastewater. Broadly characterizing many of these classes of organisms and their growth and chemical formulations, it is reasonably possible to come up with a set of equations which adequately expresses the performance of a system such as an ASM1. When we start looking at the nitrogen and phosphorus balances and the basic carbon parameters, which were developed as part of ASM2 and ASM3, gets a little more complex. Basically what you're looking at, they've chosen COD because COD is a reliable measure. So you have, these are your various fractions of, some of your COD is biodegradable, some of it's soluble, some of it's particulate. Non-biodegradable, active biomass, heterotrophs, autotrophs, and this comes down soluble and particulate. Now, when you transfer something like that into a Peterson matrix, it looks like that. And it's, I know it's a little bit nasty to try and read from where you are, but this is the same sort of formulation that we saw here. Various parameters here, and then these are the process rates over here. So they can take this section and multiply it and solve the equations. If you start considering, and this was just simply for carbon and the soluble fractions of carbon. If you start looking at something that's much more esoteric, like carbon and nitrogen and phosphorus removals, the equation tends to get a little more hairy. And I'm not going to go.
Thank you.
I'm not going to go into that. Just to show you that the matrix for an activated sludge system is rather complex. One of the other interesting challenges here is biological modeling. You have dynamic biological models, and what happens is your influent is not steady. So your influent, this is diurnal flow over a period of 24 hours. This is what your actual wastewater generation looks like at most plants. And you'll have changes in each of these, you have changes in your variables, and along with the changes in your flows. And it, like I said, can get really, really, really messy. All right. We were going to switch to a demonstration of some software, but we couldn't do that because of an incompatibility problem. But here was I took this Sumo software and made a little model here. Influent, grit chamber, that goes to waste, that's mostly inert. It's the sands and stones and all that. Then you have a stirred reactor, it can be aerated. Then you go to a clarifier, sludge comes down, and then it's recycled. Some of the sludge is wasted, and you go out to the effluent. And to do this dynamically is no mean stunt. If you get a little more complex and start to worry about things like nitrogen and other things, you start to get into something a little more complex. And this is a Bardenfoe plant. And it's designed to reduce phosphorus and nitrogen. And so what happens is you start with your influent. This is a large grit chamber. Then you go into an anaerobic section. And the anaerobic section takes out the phosphorus, causes the cells to pick up phosphorus. Then you go into aerobic, or anoxic, and then you finally go into aerobic, and then do some recycle. There's a final aerobic section. Then you take your sludge out, drop it in, and then some of it gets recycled back to the front end. It's extremely complex. It's extremely complex. That's why, that's what the Bardenfoe system is. There's probably half a dozen different types of systems that you can use for nitrogen and phosphorus removal. I should mention, the reason for nitrogen and phosphorus removal is nitrogen, usually the principal hazard there is ammonia. Ammonia is an aquatic toxin. Small amounts of ammonia can really ruin a fish's good day. Phosphorus is as little as 0.02 milligrams per liter of phosphorus in a water course can cause an algal bloom. Once you get an algal bloom, you get this nice green scum all over the top of the water. And what happens is when there's sunlight on the algae, it produces all kinds of of oxygen because of chlorophyll. But at night, the bacteria don't stop. They just take the oxygen right back out. So you wind up with a huge up and down variation of oxygen levels. And that results in fish kills and everything else.
These are chemicals from the fertilizers you're putting on.
Well, it's fertilizers, but for example, you use in some cases you use phosphate detergent in your clothes. That's what makes it nice and white. If you walk into a room where there is UV light and you see the shirts kind of glowing bluish white, that's phosphorus. It's phosphate.
White the white shirts.
Yeah. And so there's phosphorus in all kinds of things. It's a natural element. It just so happens that it is one of the problems in trying to keep it out of the water course. In other words, for example, we all take in phosphorus. We all excrete phosphorus. We excrete phosphorus. We excrete nitrogen. We excrete carbon and many other things, along with personal care products, and you name it. And all these go where? Primarily into the sewer, and they wind up at the treatment plant.
Not to mention the medicines.
Yeah, well, personal care products would include the medicines, and some of them are good, and pesticides and everything else that's dumped down the drain. So, anyhow, components of that previous thing include primary sediment and grit removal. Let me go back to that slide. I can do it from there. Primary sediment and grit removal. Anaerobic treatment to help reduce phosphorus by getting the bacteria to take it up. Anoxic reactor to reduce the nitrate and absorb excess phosphorus into the biomass. Aerobic reactor to reduce the carbon fraction of the waste. Final clarifier to reduce the total suspended solids and help keep the bacteria in the system and sludge return and recycle. All this is dynamic in the real world and is dynamic in a modeling environment. And one of the things I had planned to do was run a little model of this software that's called Sumo. And it's very highly graphical and it's really kind of neat to watch it, but we can't do it as far as
Out of curiosity, are you in favor of garbage disposal or not? Is that good or bad?
It's a bit of a trade-off because in one place you're sending lots and lots of stuff down to the wastewater treatment plant. In the other case, you're sending it to the landfill. And so you kind of have to balance the two. I'd love to see us go to a much more comprehensive design where we integrate our landfill. I've seen anaerobic digesters in solid garbage, basically, garbage waste. They take and anaerobically digest. A few years back, I helped design a very compact composting reactor based as a way to help a municipality get rid of their sewage sludge by making a fertilizer, a soil amendment. So there's all kinds of these possibilities. It's just that everyone is just slightly different. Yeah.
I see a bunch of electrical engineers, us who are non-seasoned civil engineers. I'm just wondering about the tap water. I mean, it's getting harder and harder just to have
Well,
drinkable water.
your requirements for your tap water are very closely monitored. If you want to find out what's in your tap water, go to your county and probably on their website somewhere, they have what is called a Consumer Confidence Report, CCR. This is an annual document that has to be made public it's a summary of their modeling.
Is it worth anything? I mean,
Yeah, it is. I have to prepare them annually for a small trailer park. And I look at the data and it tells me, yeah, okay, they're doing a pretty good job. They don't have a problem with water quality. But I watch the water quality to find out what's there and whether or not it changes from year to year to year. So
these purifiers you put on your faucet, are they worth? Is this marketing or is it?
no, it's not marketing. It's a regulatory requirement. So there's a whole part of EPD down at downtown that does nothing but look at these CCR reports.
No, I'm talking about when you go to some store and you buy something and you bring back to your residence to get water.
Oh.
Does that work sweet?
Yeah, generally speaking, it is. My caution would be look at the source. Don't look at the marketing. Usually on each of those little gallon or 5-gallon containers, they have this water, the source of this water is. You'd be amazed at how many of those containers have source of this water is XYZ municipal.
Well, you're talking about bottled water. I think he's talking about add-on consumer.
Home filtration system.
Yeah, I'm talking
Oh,
about,
okay,
I'm talking
all right.
about both. Buy bottled water and full filtration.
All right,
Is that just marketing BS
if
or-
you're talking about home filtration systems, there are basically two types. One, there's a carbon system, and the other one is a membrane system. They both do a similar job, but with slightly different techniques. The carbon system is very much like pouring sand into a bucket. the bucket holds a certain finite amount of sand, just as the carbon filtration system will hold a certain type of a certain amount of types of chemicals. Whereas the membrane system is much more, let's see if I can characterize it. What happens is the membrane system is like a great big filter, super, super fine filter that you have to, they're about 80 to 90% efficient in some cases. They do a wonderful job of removing certain types of pollutants. I've designed a few of them, and yeah, you can use those quite well. But the thing is that for every, let's say, 100 gallons that you pump through this, you may lose 5 to 10 gallons, just from the standpoint of it's a question of osmotic pressures. And the membrane leaves all the dirty stuff on one side and allows the clean stuff to pass. Well, but it has to get rid of a certain amount of that dirty stuff so that it can continue to maintain its porosity.
Backflush.
It's not a backflush. No, it's really a continuous bleed.
So ideally what you do is you replenish your raw side every so often. Don't just keep recycling.
Well,
the raw side.
on your carbon system, you're going to have to replace your cartridge. On your membrane system, what happens is they have a separate tap that goes to the is connected to the waistline. So you process 100 gallons, you get maybe 90 and maybe 10 gallons go back into the system, into the sewer system.
Reverse osmosis.
Yeah. What about it?
I mean, that's what you're describing.
Kind of. It's a lower pressure. In other words, reverse osmosis is primarily for large heavy seawater plants and things like that. And the RO systems generally run at 500, 600 PSI. And you have to do a lot of pre-treatment before that, but they come up with a pretty good solution. You can't get everything, but this is a form of lower pressure that you can get with some of these membrane systems. There have been many improvements in the past few years, and you can get the membrane systems that'll operate at basically your household pressures, which is 50 psi or less.
Yeah, they sell them for the home.
Yeah.
And they have those too. They don't need to waste wine either. They're just
Some of them.
disposable cartridges.
Yeah,
Toss them
okay.
every 6 months or whatever.
Yeah.
I have a question about modeling. About a year ago, there was a presentation about global warming and climate change. And someone in the audience who said he was an expert in modeling, he said he could create any kind of model to suit or validate any preconceived conclusions. My question is it likely or possible for someone to create a model to suit whatever conclusions you want?
Let me answer that this way. I'm going to take you back to integral calculus. Okay? Every time you have an integral, as a way of solving an equation, when you have an integral, you get a constant. Okay? If you have a second degree or two integrals, you have a constant plus an x term with another constant times a function and a third constant. So it's quite possible. I mean, I don't trust the mathematical modeling of the environment because it's just too open. And I think many of the people, and I know this will be controversial, but I think many of the people who are doing the mathematical modeling have a vested interest in one form or another in the outcome. And so it may not be a conscious bias, it may be a subconscious bias, but I think it is biased. I mean, if you look back at the IPCC reports over the past few years, that's the International Pollution Control Committee. At one point, they were estimating a 3-meter rise in the water levels. The last one I saw, I haven't seen the latest one, but I understand it's now down to about 6 inches to a foot. That's a huge difference when you consider the amount of water that's on the earth. So it needs to be taken, things like that need to be taken with a huge amount of salt. Maybe not a whole mountain, but several grains. And so you need to be skeptical. And the best advice I can say is figure out whose axe is being ground, because that will tell you where the money is where you're going to get the results. The studies will follow the money, because you fund what you want, and that's just human nature.
Minutes wrap up.
I'm all done. Thank you all. Appreciate it.
We hope you enjoyed this recorded presentation given at one of the Atlanta Metro Chapter meetings of the Georgia Society of Professional Engineers, an affiliate of the National Society of Professional Engineers. To find out more about us or to join us, check us out at gspe.org.